So good morning, everybody. Welcome to this morning's Mineralogical Society Skills and Training session. This morning's talk is being given by Daniel Rayner, Peter Horton, and Robert Bannister, talking about single crystal X-ray and 3D electron diffraction techniques. And I'll start by saying thank you to the three guys for coming along to do this morning and preparing it for us. We appreciate the effort that goes into that. I'm going to hand over to Peter in a moment, but just briefly before we start, I wanted to tell those of you who are not familiar with the Society a little bit about us. Society founded 150 years ago. We have about 800 members, individual members. We publish 3 journals. We have 8 special interest groups. We run 8 or 10 research in progress type meetings every year, and we also host international conferences every few years. We did one last year and one year before the European Mineralogical Conference. Membership for students is free for 3 years, so get yourself signed up in order to help benefit from what we offer, including a free subscription to Elements magazine. Many of you will have heard of that one. It's got about 15,000 readers around the world at this stage. So a popular magazine for those of you working in the geosciences. We also offer bursaries and grants for people, to students in particular, to help you get to conferences and so on. So www.minersoc.org if you want to check us out. We'd be delighted to welcome you on board. Having said all that, I'm happy now to pass over to Peter first and allow him to introduce his co-speakers and lay out what's going to happen for the next hour or so. Peter, thank you.
Okay, Kevin, thank you very much for your kind introduction and allowing us to talk. Basically, it will be myself and Dan giving most of the talk. Right, so the outline of the talk, so I'll give a brief introduction to crystallography, what is diffraction, difference between powder and single crystal. I'll spend most of my time talking about single crystal X-ray diffraction, what we're looking for, what we can achieve, then a brief introduction to National Crystallography Service, the NCS, before Dan will take over and give discussion on electron diffraction and how that works seamlessly with X-rays as well, different things. So, very brief history. X-rays discovered sort of 1895, so just over 130 years ago, and sort of only sort of found just over 100 years that actually you can have diffraction as well in the crystal, and that actually you can determine the crystal structures from these diffraction patterns. And one of the more recent things is actually sort of once you have these diffraction patterns, you can get a lot of work with it. And one of the more famous things is sort of 1950, sort of Rosalind Franklin, Watson and Crick discovering the overall structure of DNA, sort of the double helix, and so on. However, crystals themselves have been held in reverence sort of throughout human history. Sort of some of the earliest artifacts are sort of crystals, their shapes, sort of just having these nice smooth edges and everything else. And actually, a lot of the fundamentals of crystallography were done before we could actually have X-rays and probe the internal structure. So people knew things about what was going on inside just by sheer looking at them and so on. So, let's see. What is diffraction? So we use diffraction, and diffraction is a property of any wave, any wave that passes between an object, sort of between objects of similar size, sort of to the actual wavelength of the wave, you will see observed diffraction. And if multiple objects are sort of pass by, you end up with interference patterns. So on a very simple level, we have 5 spots, put the thing, diffraction, we'll see a smear. If we get more, we'll get a grid. And if we have a 3D array, we'll get a 3D reflection of spots. Now, that's how diffraction works, and it works on any type of wave. We're interested in looking at what's inside sort of crystals, what's inside and at the atomic level. And generally, the distance between atoms is the order of 10 to the minus 10 meters, which is sort of 1 angstrom, 0.1 nanometers. And the wavelength of light that allows us sort of is similar to that in the electromagnetic spectrum is actually X-rays, sort of hence why we need X-rays. We also have an issue that we generally prefer the X-rays to be monochromatic, so we only want a single wavelength. So we have to make sure all the other wavelengths are removed. And diffraction is actually a weak effect. So at least for X-rays going through, 99% of the beam will pass straight through a crystal without affecting it at all, without interfering. And so we collect only a small amount of the diffracted, so the diffracted beam is only a small percentage of what's going on. And the other thing, the X-rays, although it's based on sort of spacing between atoms, what they actually interact with is the electron cloud. So we're looking at the number of electrons have an effect on how the diffraction occurs. So you can imagine sort of very light elements, so especially hydrogen with one electron, it's moving around, sort of doesn't give much diffraction, whereas the heavier elements give a lot more diffraction and much easier to be observed. But that is diffraction. So we now have, when people talk about X-ray diffraction, they generally talk about either powder diffraction or single crystal diffraction. So what is the difference? If you have a powder, you have lots and lots of tiny crystallites and sub things, and when the diffraction occurs, you effectively, if you had a large enough detector, you would see sort of circular rings on a 2D surface. Effectively, you're actually generating entire spheres, but we only actually observe circle, and the detectors themselves are normally just a thin slit. So actually what we get is a thin light. So we get the intensity and we measure it based on the angle, how far it's diffracted out away from the crystallites. And powder is a bulk technique, so we can put large, well, compared to single crystal, you can put large amounts of sample down and you actually want to get it, and you can get, as I say, significant information. We can get the unit cell, sometimes you can even get structure. And as I say, it is a very useful sort of these patterns are pretty much fingerprints. So you can normally, if you've pattern matching, you can normally tell whether the structures are the same or at least different from something already known. Now, for single crystal, effectively the same thing occurs, but instead of getting the circles, we now get individual peaks. And these spots are related to actually what's inside the atom itself. So if you think about it, we've got our pattern, our sort of 2D pattern, we can get it, and it's exactly the same as the spots, but because we've got individual information, we've now, instead of being a 2D thing, we've now got 3D, possibly even 4D information. So we get a lot more information. And the single crystal allows us actually, those spots, their intensities and everything else gives us information about the composition of what's inside. And it's much easier to determine that from the spots than it is from the powder pattern. So for there, you've munged a lot of sort of information together. You've compressed it down. So yeah, we've got powder is 2D, and I think it's 3D. Now I've been talking about something that's crystalline, and the most important part of the techniques, both powder and single crystal, is we need a crystalline material. And basically, what we have is we want something that has long range order. So that means that the atoms inside are arranged in such a way that if you transpose yourself, translated certain distance away, you'd see exactly the same thing. So here, sort of, as I say, very simple examples. Silica, you can either have silica glass as amorphous. Technically, it will diffract, but you'll just see a lump and just one broad peak over the entire diffraction pattern. And you can get information, but not much. Whereas what we actually want is crystallites where we actually can index individual peaks and we can get information out of them in single crystal. So now, so what is actually a crystalline solid? Crystalline solids have the atoms, whatever's inside it, arranged in a regular three-dimensional array. When we're discussing what's going on, we consider crystals that are perfect. And the perfect crystals do not exist in the real world. So there's always imperfections, there's defects. The crystals, sort of the atoms inside the crystal vibrate. We see them at room temperature, possibly a low temperature. We never see them at absolute zero. So all the atoms are vibrating. So a perfect crystal we use it for the maths and everything else, but they do not exist. But actually, it helps a little in seeing what's going on. Um, but the basic idea is you have a fundamental repeat unit you can see in sort of that can be mathematically constructed inside the crystal, and then that is repeated in all three dimensions, and you can effectively, if you had to, build up the crystal back to what you can actually see and things. And we need that regular translation. So what we have is as I say, is a mathematical construct called the unit cell. Doesn't actually exist within a crystal, but we can use it to actually define sort of positions of atoms and so on, and then use their translations. So as I say, it's just a 3D parallelepiped, and sort of the A, B, and C are your lengths, and your alpha, beta, and gamma are your angles. The simplest version of this, if you think about it, will be a cube where A, B, and C are all the same, and your alpha, beta, and gamma are all 90 degrees. And you think about cubes, even sort of things like a dice, you can easily pack them and just keep repeating the pattern throughout. There are sort of, again, mathematically, no, there are seven shapes where you can do this, different sort of orientations of sort of whether you have A, B, and C, alpha, beta, and gamma equal or different. But the important thing is this brick, this unit cell, is tiny, and even on the small crystals. So if you think about it, a 10 by 10 by 10 micron size crystal, there'll still probably be at least a billion unit cells inside. So we're sort of, and basically when we're actually solving structures, doing everything else with it, we only have to consider the unit cell. We don't have to consider sort of all the repeats. And if you think about it, averaging over a billion, so you will, as I say, we will see the average and nothing else. So we need it to be the same, but it's just everything will be an average and things. So we're always observing averages. However, if the crystal has this 3D array and has the repeat unit and the translations are good, we can actually define really very well where the atoms are. So we can define an origin. We can say, right, these atoms, fractional coordinates within the unit cell, and everything will work fine, hopefully. So this comes back to going for diffraction. If you think about it, all those atoms are in nicely defined things. The gaps between them are always the same. Therefore, when we fire our X-rays at them, we get our 3D grid. Perfect. But that's why we need X-rays and why diffraction works, and so on. Now, I'm afraid this bit gets into a small bit of maths. I'm hoping there won't be too much and two things, but the easiest way of thinking, right, we say diffraction occurs. How do we know where those spots will appear in space? And actually, it can be used by Bragg's law. Sort of those sort of two sort of people who got Nobel Prize and did the first crystal structure discovered that actually, sort of, if we think about instead of having just diffraction, we think about planes within the unit cell and reflections. It actually works fine. So again, we are placing imaginary sort of mathematical constructs, these sort of planes with sort of mirrors within the crystal, so to get these diffraction angles. Now, and get reflections. And the one thing that's actually observed is only at very specific angles and at specific distances will you actually observe a reflection. So we call them often call spots reflections simply because of this, that we assume there's mirrors and so on. The equation is sort of the distance between these planes and the angle, and you have an integer here. And the other bit here is actually this lambda is the wavelength of the X-rays used. So depending on what type of wavelength of X-ray you have will determine the distances between these spots as well. Basically, we need a path difference and we need sort of interference patterns, and we only observe them when the actual patterns of this distance here is the same as one wavelength or two wavelengths or things or an integer number. Simple. Now, each reflection where they are in space tells us information about the unit cell. So very quickly, sort of couple of images or somewhere else, we should be able to get information to say exactly what the unit cell is. So those 3 dimensions, sorry, 6 dimensions are the 3 lengths and 3 angles. However, we also get extra information. So the intensity of each of those spots will vary depending on the atoms inside the crystal, inside the unit cell, and how they're positioned will affect the thing. So I said before that X-rays are affected by sort of elements and different things. Each atom within the unit cell will affect things. So we'll get strong peaks, weak peaks. There may be peaks that just do not appear because of sort of how the things are added together. And the one thing we actually measure very easily, we measure how intense those spots are on the screen. That's what we actually measure. Unfortunately, to do the maths, we need the structure factors at the end, and there's a whole load of um, constants and things that actually change the intensity of the that we actually measure. However, we can actually assign or calculate all of these to get this value here. And this is the one we actually want to use, which is good. Now, that structure is related to all the atoms in the structure. Every single one of them will scatter and produce something to do with those waves. So it's tiny amounts, but of course, because we've got billions of atoms, sometimes things, they all add together. And we can reduce it down to something that's actually sensible to work. Because if you were trying to calculate and say, okay, we have a billion atoms and they're all related to this structure, we'd have no chance of getting anything to work at all. But luckily, we can condense it down. However, to get all that information, we need to sum over all the waves that are possible, all these FK, and we need to collect thousands of images. So, sorry, thousands of these reflections to get all that information. Everything is an average, but we hopefully will get everything else. So the result of all that, which is probably easier, that's most of the maths done, is what we see on the screen. So here is a single diffraction image. So we see lots of spots. You can see there is some sort of grid. You can see these are nicely sort of look as though they're aligned. There's the same distance apart and the same this way. It's a similar distance apart. And that is because we're seeing an inverse of the unit cell here. So how far the end things, but we have direct information to see that actually we're going to have yeah, the crystal's actually working quite well. Now, this is one image. We actually need to be able to rotate the crystal in all 3 dimensions and collect these images, having sort of effectively bathed in all dimensions, just to make sure we can collect what's effectively called a sphere of data, or at least a truncation of it, to get all the information we need. So generally, we need to collect hundreds, possibly thousands of images, and then combine them together. So normally, sort of nowadays, the actual data collection can take sort of anywhere from sort of 15, 20 minutes, or still can be a couple of days. Whereas in the past, you'd be talking sort of 2 or 3 days. You might be having to get everything on electronic film and then measure each of these spots by hand and work out how its intensity varied from the one next to it. And you can imagine why it took sometimes 6 months, years possibly to actually solve crystal structures, whereas now they can be done a lot quicker. But we hopefully get all our images, and this is the final horrible math slide I'm going to produce. We have a whole load of equations. We have straight Fourier transform and a reverse Fourier transform and equations of how all these atoms are summated to get the crystal structure. This looks horrible. There's complex numbers and other things. I'll do it in a different way. We have our crystal. We get our observed diffraction. This is a slice. And this works. So this is what we actually do. This is our experiment. Now, if you have a crystal structure, it is actually the inverse Fourier transform will allow us to calculate a diffraction pattern. And that, again, that is very trivial, simple to do. In fact, it happens all the time. The one thing we can't do directly is take this pattern and therefore actually calculate the structure. So what we do instead, so we have this thing called the phase problem, and we lose this information when we're collecting the data, and we've got to generate it again. So what we do is we propose a model, calculate its diffraction pattern, compare it to the actual diffraction pattern we collected, see how good a fit it is, tweak it to make it better, and then go back and hopefully have a better pattern and so on. So when we're actually talking about crystal structures, we are talking about crystal structure models and how well they fit. So the one thing is, this is mathematical equations. We can put any model, we can propose any model we like, and it will generate a calculated diffraction pattern. How well it fits the actual measured pattern is another matter, but you can always generate, so you can always propose a model and generate a pattern. What we want, of course, is these to be as similar as possible, and there's least squares refinements that actually see how well they fit. But it is always an iterative process. It's not a one step, here's the pattern, here's the result, and so on. Now, I would say computers now can do a lot of these iterative steps for us, so it's a lot quicker. But in the end, there's always an eye just to check that actually they have picked the things, because the one bit that can be important is the chemical knowledge and just checking that what has been made is actually physically possible, because these structure models you can project, as I say, mathematically you can do anything you like with them. So we need to make sure actually it's chemically sensible and physically possible when it is actually preparing the pattern. So how are we doing? I've got the single crystal experiment. So we want to select a mount a crystal, which is actually probably one of the most tricky jobs. We then get the unit cell and get the geometry. The one thing is, if we know where the spots are going to be, we can set the collection to actually move the crystal to make sure every single reflection is collected. We then apply all these corrections. We solve the structure, complete sort of do this, complete the structure, make sure all the things, so then refine the model, and hopefully at the end we'll have a structure that's correct and we'll be able to interpret the results. The one thing from a crystal structure is you get a lot of extra information. So we will know not only the atoms involved, so which elements they will be, but also how far apart they are. So you can get things like bond lengths, angles, geometry, and it's a 3D representation. So you can, if you're lucky, you can get sort of chirality as well and know a lot of things about the structure and see how far sort of atoms are apart. And sometimes it can be useful for other techniques or things of if you're looking to see, I need these metals to be so far apart in my refining thing, actually, are they or not? And you'll be able to find that information out. So, I want a crystal, the perfect crystal for an X-ray structure. So, okay, it's got to be crystalline, that's fine. We want one crystal. The technique works, you can get away with we want one crystal, it works much better. So if you've got a twin or you've got one crystal that's much larger and a little tiny side bit, you'll probably have to get away with it. But generally, it always works better for a single. We also would like the crystals to be spherical. It helps in a lot of the scattering effects and sort of things we have to do. However, normally crystals are not spherical. The closer you can get is probably a cube. Sorry, yeah, a cube, but a lot of them are plates or needles or anything else. But we can get away with things, but we would like something spherical, as I say, just to have the dimension. We'd like it free from defects and no strain as well. And the size, realistically, sort of it depends on what the material is and everything else. Largest we probably want is 0.5 mm, sort of in a certain dimension. Normally, we're looking at 100 microns. 100 micron diameter sphere would be absolutely perfect. So normally, sort of anything larger in the dimensions normally doesn't actually get bathed in the X-ray, so it's not actually getting diffracted. And there is a thing of gets down to a certain stage where sort of once you've got 2 to 3 microns, we just are not seeing enough diffraction. It does depend on the material and sort of the heavier elements, you'll be able to go look a lot smaller. Sort of if your material contains sort of, I don't know, gold, mercury, something like that, then you can always get away with a much smaller crystal than if the heaviest thing in there is something like carbon. Now, that's what we want for a perfect crystal. This is what we actually get. And I think pretty much all of these in some form we've managed to get diffraction and probably get structures on them. So say it can be the sort of thing. The one important bit is we want to make sure we get the crystal on its own. So a lot of these you can see we have crystallites together. So these are needles, my cells. Again, these are needles that are grown together. This is plates grown together. We want one crystal by itself. This is probably a twin. We can cut it up and so on. But all of these, they are crystalline. They will diffract in some way. Let's see. So very quickly, we want to try and select a crystal. We look at them under the microscope. We generally hold them in oil, use acupuncture needles for actually manipulating them to try and separate it. Because as I say, we want to choose one crystal, isolate it from the bulk, and choose that one, pick it up. The pips we use are now a mitogen, which is almost X-ray transparent. It's amorphous sort of plastic, but basically we want to try and mount the crystal in so that the only thing diffracting X-rays is the crystal and not the grease, not the oil, and really not the fiber or anything else. But we've got to have something to hold the crystal, so we want to minimize what else is in the beam and sort of thing. So this one, crystals mounted fine. You can see all this lump of solid underneath. That will cause problems with the X-ray beam. We'll get a lot of diffuse diffraction off that, sort of that can change our images. So this one actually, although it's a very thin needle mounted, was probably a thing because we can fire the X-rays up here and actually have almost purely the crystal in the beam and nothing else. So sometimes things, but yeah, we want one crystal on its own. It's another thing. One of the things you can have is loops. We've got it thing, and we have our diffraction pattern, and we always test it just to see that actually it's diffracting well. So again, we can see the spots on the screen. Each of these reflections, we can see the rows. They look as they're matching, distance apart, and we want to get the intensity is correct. We want to see on our image that it actually diffracts all the way out. We can see these things. So the final thing on here, this is the beam stop. As I said, 99% of the X-rays go straight through the crystal without doing anything, and they would damage the detectors. So the one thing we do, we have a beam stop, and again, this causes a small issue, but again, it can be masked out and removed from the calculations. But we just say this is a perfect thing. So how do we actually collect the data? So this is our recent example, goniometer. So X-rays are generated over here, things, and rotating anode, fired and come out of this thing that looks like the pen here and hit the crystal. So it's right on the end of this loop here. So you may be able to see the tip of the needle, but there's nothing else there. There's a beam stop, and here's our detector. Generally, the one thing we do, we cool our crystals down. The standard measurement is 100K, sort of at 100 Kelvin. This means that we've cooled the vibrations, so we've got less thermal vibration going on. Generally, we freeze the crystal into a thing, and if there's damaging by the X-rays, normally at 100K, most often this will not occur, not always, but with things. So we have our crystal on the loop, and then we can move the crystal. The whole point of these goniometers is they can move in multiple directions. So we have phi. This rotates the crystal on the axis of the pip itself, so it just rotates around here. You then have kappa. This swings basically this way, and moves the whole arm up and down. You then have 2 theta. This theta actually moves the detector. So again, where you're actually measuring, where you're detecting the crystal. So again, it can move around left and right. We can actually move the detector in and out, which will give us things of sometimes we may want to have the spots too close together, so we move it out or move it in. And finally, we have omega, where we move the whole base of the goniometer, so the whole thing will move in relation to itself. Now, the one thing to note is only when kappa is at 0, so it's sitting on the top, will omega and phi actually intersect, so you'd be doing the same motion for both omega and phi. So the rest of the time, if you move phi and omega, you'll get different positions. So with this, generally the coverage of sort of crystal, we can move it around to pretty much get the crystal to exist in any position in relation to the beam and then detect it. So we collect our images. We collect our thousands of it, well, hundreds, possibly thousands of images. We measure their intensities. It's nicely done by the computer for us, how strong they are. And the result, so we do a whole load of corrections, and the result is just an H, so effectively is a file of corrected intensities, which is thousands of lines long, but each one has its own unique identifier. So we have coordinates, which are where it is on the detector in space, and these are HKL, and they're related to the HKL we see here. Then we have the intensity, and then we have an error on the intensity. And this is basically what we do. We reduce all these images that generally will come to sort of a few gig of data and reduce it down to a single file that's generally sort of somewhere between 1 and 10 meg. Now, there is extra information we're moving out, but normally 90%, 95% of the time, this is all the information we need to get our things. So, solving a structure, we've measured the intensities. We now try and solve this phase problem. So we try and get a solution, and then we start refining. We get the heavier elements first, then we get the lighter elements. Finally, at the end, we may find hydrogens, and then final bit is to get some analysis. So what are we doing? When we're solving a structure, we assume we've got our things correct. So hopefully, the electron density, if we have the right phases, we'll get a structure. If we have the wrong phases, you can see this is something with it correct, this is something with it completely wrong, how the map just looks like a mess. Hopefully people can still recognize contour maps, see how these things are. And even if we start with some phases and get the same heavier stuff, we can see that there's something going on, so this one is correct. Our maps we have, just do this one. We have just observed maps, so we can see our intensities. Okay, this is a 2D plate, and our crystal structures are 3D, but we can rotate around and see where they are. But you can see that the sulfurs in this structure and all the carbon atoms fit quite well. This area here, there's something going on, but we can't see it. So one of the things we do instead is we do difference maps, where we actually take our observed and remove it from the calculator and see what's left. So this is basically what electron density is left. And here we can now it suddenly becomes much more obvious that there's something here and there's an atom we should be actually putting in the structure and improving it. So how do we know that we're doing well? One of the most important things is the R factor, and this is just how we monitor the cycles. And it's just checking that the actual observed against the calculated, how well they actually fit. So we have our observed data, and this is the stuff that's calculated, and how different actually are they. And generally, by the end of refinement, hopefully for us, at least for a good X-ray structure, we want to be between sort of 0.02 and 0.07. So it's 2 and 7% error on our things. We're never perfect because we can't collect all the data and we have a whole load of different things and things. So we're never going to be perfect with the structure, but normally it comes out quite well. But once we've got all this data, we have, as I say, we'll have our unit cell dimensions, which we compare, and they can be used to compare against powder patterns or anything else that you've already got, and just check they're the same. We get a list of atomic coordinates, what atom types they are, and as I say, we can derive all these secondary parameters. And we put this all in something called the crystallographic information file. It's a defined format. It's been around at least 50 years, if not longer. And basically, it means every single crystal structure in the world will put these in this one format. So anybody in the world can transfer this format and ask for their crystal, and they'll always be given a CIF. It is text readable, so it is just a text file, but it is very much set for computers to read rather than humans, but it is set in a way that you can actually read it as well. And there's various checks to make sure that actually everything in the structure does make itself. But the final thing, hopefully, is an output where we've got the information, we've got the crystal structure. So that was, I hope, a whistle-stop tour of doing how to get crystal structure. So finally, I work for the NCS, the National Crystallography Service. So what is it? You see its remit here to provide advanced high-level facilities and expertise beyond that which is available and affordable in the normal lab. It has been serving the UK scientific community since it was set up by Professor Mike Hursthouse, officially in 1980, but there were collaborations that sort of things for at least 10 years before that, where there were samples sent between different universities, which Mike would run, and so on, officially. And it's been in Southampton since 1998, and currently sort of under the leadership of Professor Simon Coles. So our diffractometers now, we have two main. We have 007 copper sources, we got and an FRE molybdenum X-ray source. So having two different sources, there's combinations where changing the X-ray wavelengths, or if you can't do it, sort of you are stuck. Each element and each diffractometer is stuck with a single wavelength, and we can only adjust it. So it's useful having two different wavelengths so we can look at things differently. So some crystalline materials work better with one source compared to the other, and you can get different information out. We have high pixel detectors. So these are hybrid pixel detectors. So we basically have pretty much no noise and can do continuous collections. So the dead time between images is on the order of nanoseconds or something ridiculously small. So basically you can almost watch things. And the optics allow us to sort of get high flux onto the crystal and get more beam. Our general data collections, most of the time we run 100K. We can go sort of above room temperature up to 500K to run our collections, but basically the thermal motion is, unless we need to, we'll always try and run at 100K. And our typical thing is to actually, yes, the audience we've got either anybody in the UK who's eligible to get an EPSSE grant is available to use the service. So we have unsupported scientists, so scientists at universities where they don't have their own diffractometer. We can provide help with the crystallography and so on. We'll also help existing crystallographers or things because we can have access. Sort of our equipment is some of the most powerful in the country and some of the top in the world as well. So we can sort of use our facilities and help them. And sort of we can do rapid collections. We can handle sort of non-standard samples. So anything that's sort of air sensitive, temperature sensitive, moisture sensitive. And there is a group of crystallographers sort of, we'll say, yeah, highly trained to help out. So some of the things we can do sort of, let's say, something very simple, systematic structures. So some people, when they do sort of with crystal structures, you just want to change one thing and see how the structure changes, and you want to get a library of these, and we can make sure we can help sort of get the entire library. Just sort of sometimes because half the crystal structures easy to find, then the other half, because it's more complex things going on, we'll be able to look at the four sort of samples in the series. We can look at phase transitions within crystals as well. So here is a crystal that has three phase transitions. So it goes, if you're really sort of observant, you may be able to see the subtle differences between these structures, how they change. It's basically just shifting. So if you've got layers and they shift against each other or change slightly their tilts, and this is a reversible process, so we can just follow this by the X-rays. Yes, we see the average, but we can determine when they occur and so on. So we can look at sort of things. That's with temperature. We can also do the same thing with pressure. So here, the bromide of the chemical at low pressure is identical, sort of is isostructural to the chloride. At high pressure, it's isostructural to the iodide product. And as you increase the pressure, sort of we'll see the change. So these diamond anvil cells, you can get sort of they're sort of not the easiest thing to use, but you can sort of create reasonably high pressures very simply because you're compressing a very small amount of material in a very sort of things space. So we can get those. We do work with gases of not under very high pressures. So generally it's just a couple of at most a couple of atmospheres, but we can see sort of one of the things of there's MOF structures where a lot of things is going, what's going on inside? Can they absorb stuff? Can they things? And so we can look and see whether gases are absorbed inside crystals and how that affects the crystal structure. And finally, we can also do some very high resolution analysis. So when we look at the X-rays, we're normally just looking at where the atoms are, look at things, but we are interacting with the electron cloud, and if we have high enough resolution data, we can actually look at some of the information about how the binding occurs. So basically, this will be how strong some of these bonds are as well. Yeah. And at that stage, I will pass over to Dan to tell you all about electron diffraction.
All right, thanks, Pete. Yes, so now we heard what all the fancy things that the NCS can do. So what can it not do? Not more. No, there we go. And so just basically a recap of what Pete said. So single crystal XRD has some limitations. So we need crystals for a single crystal XRD that are at least 2 to 3 microns in size, ideally even 100 microns. And this is analysis obviously on a single particle. So there's no bulk information, which there's obviously a PXRD, which can provide this. But at the NCS, what we provide is a single crystal service. So these limitations are inherent to the technique to single crystal XRD, right? So what about particles like this one shown here? That is roughly 500 nanometers now in size. And possibly obvious, or one possibility is, well, since we're limited by X-rays themselves, well, one could possibly change the radiation source. That's obviously not that trivial, but yeah. And now this is where electron diffraction comes into play. Now a brief recap of what type of diffraction sources are in principle available. Like we just said, there's XRD, I call them here reliable parents. So single crystal XRD and PXRD are widely available. Basically, every university has at least one or the other or both. XRD, especially the single crystal one, is essentially the gold standard for structure determination in at least molecular crystallography, macromolecular crystallography. Essentially, if there's a crystal that's large enough to be able to measure, to be investigated, to be measured by a single crystal XRD, there's a very, very good chance. And it's a single crystal, very, very good chance that the structure can be determined. Now, this is obviously has some limitations, as I just said. An alternative to using X-rays as the radiation source is to use neutrons. I call it here the rich uncle. Neutrons. This is exceptionally an exceptionally strong way to measure specific types of measurements. However, this is only available at central facilities. So there's one place in the UK where it can do this, and that's that. Again, like if the scientific question to be answered calls for this is perfectly well suited. However, obviously this is only available in one place. I mean, there's other sites in the world where this can also be done, but obviously these are quite sought after, and so it can be quite difficult to get time and these measurements done. And now finally, obviously, this is what I'm doing. There's electron diffraction, and here I call it the weird cousin. The problem with electron diffraction has always been, in principle, this has been around, well, also like roughly 100 years. So everything that's done on a transmission electron microscope, on a TM, is electron diffraction. One can go about then and recreate images, but in principle, it's always diffraction. However, the crystallographic analysis of electron diffraction is quite time-consuming. It's quite tedious. It's quite complicated. However, instruments are quite widely available in principle. Maybe not as much as single crystal XRD, but many universities, many institutions have their own TM instrument. And so there's at least a possibility for this to be done experimentally, let's say. Now, this has typically been done on the static pattern. So one has the sample, collects one individual diffraction pattern, and that's it. Now, what I have also called it in the title is 3DD. So three-dimensional electron diffraction. Why this? And this has been possible in the past, or has been developed in the past couple of decades, because there has been quite some substantial improvements in detector technology and what's possible with software. And this means that now it's possible to perform electron diffraction in quite an analogous way as single crystal XRD has been performed. So the first publications were at in the later stage of the 2000s, where, for example, the group of Ute Kolb has been, they managed to collect such three-dimensional electron diffraction data off of a couple of inorganics and even some organic molecules on a TEM, and be able to directly ab initio solve the crystal structures in essentially the same way as has been done with single crystal XRD, well, for decades now. And this was obviously quite impressive, yeah. So then in the 2010s, several groups around, mainly in Europe, also a couple in the US, have developed their own way of doing this. In the next slide, I'll come to this a bit. And so there was quite the interest in developing this, because it's quite exciting. And in this finally led to, in the 2020s, so 2023 was the first commercially available and commercially sold dedicated electron diffractometers. So up to this point, everything that has been done was done on a TM, which has been, let's say, repurposed to do these types of diffraction experiment, which usually was often only or mainly used for imaging. But these groups have developed protocols to do this type of diffraction. And now a combination of, or a collaboration between JEOL, a TM manufacturer, and Rigaku, a single crystal or an XRD, a company that sells XRD equipment, they came together and produced this instrument. And this is also what I have here. I'll come to this later on. I actually do a live demo after, so a bit of a teaser. And this was, so we got our instrument as the third in the world in October 2023. And yeah, so currently, I think there's about 20 instruments installed worldwide. So these are still quite new. Now, in terms of methods, this is a bit of a chronology, and because so the term 3DD is basically like an umbrella term for several specific types of measurement methods. Initially, what was done, so this is here, basically a collection of static electron diffraction patterns at discrete tilt steps. So the sample was like inserted into the instrument, and then a diffraction pattern collected here, then tilted, and another one collected here, and so forth. This is relatively simple to set up, but obviously there's a lot of information missing in between these discrete tilt steps. So this was then addressed in these words here, B and C, either by adding, in addition to these mechanical tilts, to manipulate the electron beam, either in a precessing motion or just a fine beam tilt. So the precessing motion is obviously in precession electron diffraction tomography, as it's called here, and thereby probe these small volumes that would be missing if the diffraction patterns would only have been collected at these set discrete mechanical tilt steps. And finally, there's also continuous rotational electron diffraction. This is now basically the most widely used technique. And the reason for this is because it's, again, very simple. So there's no manipulation of the beam. All that happens is that the stage will be continuously rotated, and the detector collects all the time in very much the same way as it's done in single crystal XRD. And this is only possible since we now have very, very fast detectors, because without a very fast detector, what's indicated here, this so the blue part would be collected, and then there would be dead time, which again, a loss of information in between where the detector would be read out. Now, this is essentially zero with the detectors that are currently available. There's essentially no loss of information, and this makes this now the most widely used type of technique within 3DD. This is also what's used on our instrument. So what is this 3DD, and why is it great and amazing and everything? It's very much complementary to single crystal XRD. So where single crystal XRD cannot get useful diffraction information anymore due to the particle size. This is exactly where electrons or a switch to electron radiation is beneficial. Electrons interact with matter quite a lot more than X-rays do. So whereas Pete said before, basically the vast majority of X-rays that pass through the sample do not interact with matter. It's essentially the other way around with electron diffraction. So what this means, the immediate consequence is that we can get away with particles that are much smaller than would be required for XRD. So we here, as I'm saying here, roughly 10 to 1,000 nanometers. So basically, if anything, we have an upper limit to how large crystals can be, because at some point the interaction of matter with the incident electron beam is too strong, and so there's no electrons that pass through the sample anymore, because we're working in transmission geometry. And so basically all the electrons would be lost into the sample, and we can't collect any signal anymore. Now this strong interaction with matter now also leads to more complications possibly, but peculiarities, let's say. One is that due to this strong interaction, we need to perform everything in high vacuum. If our electron beam would not be held in strong vacuum, the interaction with gas molecules would be too strong and we couldn't focus anything. The same in SEM or TM. So everything always has to be done in vacuum. But this means that possibly for some materials like hydrates or other solvates or porous materials, that could be quite damaging. And similarly, also something of note is that we use for TM, actually not that powerful, but still quite strong electron beam of 200 kV acceleration voltage, and this can lead to beam damage. It's just something to be mindful of for samples. So possibly the samples degrade during a data collection. And then lastly, sorry that this was displayed right away, diffraction now doesn't occur kinematically anymore, as it is the case with X-rays, but is dynamical. I mean, we have multiple scattering, we have multiple interactions within the sample. So basically every reflection is not the result anymore of a single interaction of incident beam sample, and then the reflection can be collected, but it's the product of several of these. And this needs to be addressed, and this makes the maths quite a bit more complicated than is the case in XRD. I mean, many of the other things are literally the same, but for this part, one should take this into account for a proper analysis. However, it's not good nor bad. It's just how it is. It's just a bit more complicated. But these dynamical effects also carry with them additional information. So, for example, absolute structure, which is obviously very important for pharmaceutical compounds, for example, can be obtained directly, and there's no special consideration in, for example, in the data collection. No special considerations need to be made. Yes. Now, this is then what the instrument actually looks like. I mean, yeah, I could just unblur and we would see it here, but this is possibly for now a bit nicer. So this instrument that we have is the Reactor Synergy ED, and this has been designed and is produced as a collaboration between JL, who's a very well-known electron microscope manufacturer, and they contributed with their knowledge and the design of the EM part of it. And the other company is Rigaku, who develops and produces X-ray diffraction equipment, single crystalline powder, and also some other things. But for here, so they make their own detectors and software. So this is quite a nice collaboration, I think. And yeah, so for anyone who knows JLTM's 2100 is basically the base model of what's been used here. It's called here JM 2300 ED. It's basically an optimized TM, optimized for 3D ED. So basically everything that's not needed for electron diffraction has been removed or adapted to be better accommodating. So what we have at the top here is the electron gun. We have a lab 6 gun, so lanthanum hexaboride, and we run this typically at 200 kb. and at very low emission currents. So stronger emission currents are only necessary to get good images. For diffraction, we can go lower, and this is obviously to protect the samples more. Then we have the sample holder coming in here. So the electrons travel down, are formed into a proper beam, and then interact with the sample. And then finally, there's a zero noise hybrid pixel detector, very much like the one used for X-ray diffraction, but obviously optimized for electron diffraction, so detecting now electrons and not X-rays. And obviously, some sort of operator, in this case, me. Now, how does this now done then practically? Obviously, the samples are very small, or the individual crystals are very small, so we can't just manipulate them with acupuncture needles. So they need to be loaded on a TM grid, right? So I have it here an image, and also here. This is just you can pick them up with tweezers. It's a TM grid is roughly 3 millimeters in diameter, and it's typically a copper grid, so a grid made of some sort of metal, typically copper or gold or nickel, for example, and then coated with a thin film of carbon on top, and all of the sample will need to be held in place by the carbon, because the carbon is thin enough so that the electrons of the beam can transmit through. And what we want is, obviously, we want isolated individual single crystals. As I just said, we can't manipulate them with acupuncture needles or anything else anymore. So we need to somehow deposit the sample onto the grid directly so that they're nicely dispersed. You put the grid into the sample vial and shake it a bit. You can grind the particles between glassets and then damp the grid lightly in the solid. You can make suspensions and then drop cast the suspension on top of the grid. So then just leave a drop of your suspension on here and let the liquid evaporate. Whichever way leads to a good solution. And obviously what we want is not shown here on this side, a very overloaded grid. There's matter everywhere. What we want is something like here, where all of these dark spots, that's some of the particles, and they should be dispersed enough so that we can pinpoint and go to each of the individual crystals on this grid. And so here, just as an example, this is one of my old samples from my PhD. It's an SEM image, and so they are currently quite agglomerated, the particles, right? So I created a suspension, hopefully broke these up. And actually, this is then what it looked like on the grid on the instrument. And if you're already quite keen-eyed, you can already see it's actually not one crystal, but it's actually 3, well, hopefully crystals that lie on top of each other. But as Pete said, it's possible for the software nowadays. They're good enough to be able to separate these, and data treatment can be performed on a data collection of this as well. And in this case, so this is a sodium carboxylate. This is then what the structure looks like. And similarly to as it could be done in X-ray diffraction, also here I overlaid a difference map, what Pete said. So in this case, there's something missing in this structure model, and you can see here there's a maximum highlighted in green, and actually this is a missing hydrogen. So again, one of the properties of electron diffraction. So electrons interact with the electrostatic potential. So they interact both with the electrons and the protons of the sample. And this has, again, advantages, disadvantages. This is something to be considered. And this makes, for example, hydrogens comparatively easier to see compared, for example, to X-ray diffraction. So it's similar to neutron diffraction, more similar to neutron diffraction in this sense. Yes, and now one thing that needs to be addressed is, as I said before, there's high vacuum, and then just in general, the sample environment during the measurement is very important to be able to get out of the experiment what the user wants, right? Everything that is true for XRD is also true for electron diffraction. We can have differences with temperature, for example. We have also differences with vacuum, obviously. We still have the temperature dependence of atom movements themselves. So the lower the temperature, the more rigid the structure is, and possibly the better the structure, the resolution of atom positions. And then additionally, as we're running all of this as a national facility, so this is this is embedded essentially into the NCS, or will be very soon. We need to cater to a wide range of people, to a wide range of different research, different samples. And so how can this be addressed? Now, the standard holder that is used is this. It's basically like a large rod, and at the end is where the grids that I showed you before will go. It's basically here in this mold. So there's a clamp. You can remove the clamp and place the grid on here, like so, and then close the clamp. And now this is ready to be introduced into the instrument. This is obviously, there's nothing special about this. Maybe just to show what will happen. Then the rotation axis, we have a single rotation axis, not like an XRD where there's several. We have only one, which goes along the holder. So basically, it's literally basically the holder gets rotated around, and this is our data collection. Now this is obviously great if the sample is stable to both the beam and the vacuum. One can just use this. There's quite a large angular range available, and that's nice. Now, for samples where this is not the case, and this is actually what I basically use as my default now, similar to what Pete said in XRD, the standard is 100 Kelvin. I also usually collect with 100 Kelvin, and what I use for this is a so-called cryogenic holder, like this, where here at the end, you see this large dewar. This can be filled with liquid nitrogen. So basically, we can again load the sample or put the grid onto the holder, put it onto the into the instrument, and then cool down. If it's done in this way, the sample has still seen the vacuum at ambient temperature, and if we cool down, then the lower temperature could mitigate some of the beam damage, or just in general improve data quality, like I said, by reducing the thermal motion of atoms in the structure. Now we can also fill this front part here also with liquid nitrogen before, so we mount the sample, we mount the grids, and then fill this part and fill this part with liquid nitrogen, and therefore already have reduced the temperature, hopefully enough, so that then when the sample is and the grid is exposed to the vacuum on the instrument, and for example, it's a solvate, there's some water bound to the material. The water is not removed due to the vacuum, and we can perform a measurement. The way this works is, so this top part also has a light. It's very nice. This is what it looks like from the top. And what we have, so the holder is already inserted here, but where the grids are, this is currently retracted into the holder. So at the end, there's a screw, which then means, so the screw on the screw, the part that holds the grids is exposed. And in this case, where there's actually two grids, two slots for grids available in this case, it obviously makes all of this preparation easier. You only have to do it once for two samples. Yes, and then you open this quite easily with this tool. This clamp snaps open, you can place the grids inside and close it again, and then retract and then cool everything down. Yes, very similarly, this is not the same picture as before, but it's also cryogenic holder. So we again have to do it, but this is an air-free or vacuum transfer holder. This entire holder can be put into a glove box. So this is for if the sample is moisture or oxygen or something like this sensitive, one cannot do the sample preparation, etc., on a bench as I would typically do. So we need to do this in a glove box that's has an inert atmosphere. And the way that this works is actually, so this again can be retracted, but now it's fully extracted. And this white part at the top here is an O-ring. So basically, this up here, this is a chamber that can be sealed off, and therefore sample, if there's a grid here, will never be exposed to air. And hopefully, this protects the sample enough. So again, it's the same clamping mechanism. It can be opened, a grid can be placed in, and then we will close it. So we close the clamp and use this. It's just a plastic slider. Slide this on top and then just press down. So this is quite easy to do. So for those in the audience who have used the glove box before, it's quite it's quite it's maybe not as nice to operate, especially on the small scale. So this is made in a way so this is quite nice to do and easy to do. So even I can do it, and I'm certainly not a very experienced glove box user. There's more holders. The ones we have, we only have this additional one. This is a gas cell holder. So this is in analogy to what we can do with X-rays. In this case, this is not a grid anymore. So the sample is being placed on a chip. And then everything is assembled together, again, properly sealed. And then gas in reasonably low pressures, so like 1.5 bar, can be dosed onto the sample to see if there's gas uptake or whatever else some users want. And then there's addition holders, so we don't have these. There's a liquid cell holder. It's again similar to the gas cell, but now in liquid, so one could watch possibly like crystallization or something like this. And there's also heating and biasing holders where a current can be passed through the sample and possibly see changes due to this. Lastly, I think this came up for those of you who are aware of SEM and TM or have seen the recent talk in the seminar series as well. There's EDS. So EDS is energy dispersive X-ray spectroscopy. And this uses X-rays that are produced due to interaction of an electron beam with the sample. So these are produced all the time when a strong electron beam interacts with the sample. Basically, the way, just to recap a bit, the way this works is the electrons of the incident beam interact with the sample, have high enough energy to kick out an electron of an inner shell electron of all of the atoms in the sample. Then a higher shell electron relaxes down into the created hole, and this difference in energy is released as X-rays in the range of X-rays, and this X-ray is of a characteristic wavelength for this specific element, so therefore can be analyzed. And that means that for each of the data collections, we can do this type of experiment after, and therefore determine roughly the elemental composition of the crystal we just did the diffraction experiment on. So this is quite powerful. So in this case, this is an example of a metal organic framework, so with iron and different linkers. So this one is either just a carboxylic acid, or here there's an amino group, so with nitrogen, or a bromine group, so bromine. And you can see in the spectrum that either there's no peak for nitrogen nor for bromine, so it was just the regular carboxylic acid linker, or it was the amino linker, so there's a small peak for nitrogen, or it was the bromine, so there's a peak for bromine in the spectrum and not for nitrogen. This also works for mixed metal systems, etc. Yes. Now, actually, I will skip this part, also due to time, but mainly because this is just examples, but hopefully, so we can now move to, hopefully I prepared everything. So this is actually how everything looks. We have, I put a sample on the regular room temperature holder, intentionally something minerals. So this is a mix of supposedly of malachite and azurite, so copper carbonate hydroxide compounds. And the grid itself, this is what the grid itself looks like, right? So you have these grid bars, and then I have sampled. Maybe this is a bit overloaded in this case, but it's okay. And you see all of the dark particles. That's some particles of the sample. So this is just an overview image, and you can navigate. So all of the green spots, this is something I have been before. And now this is then what it looks like. So one can move around this grid, right? Here's a large particle, there's a smaller and even larger one, possibly agglomerate, and so forth. And just to demonstrate what I meant before with when the particle is too large, I just maybe go to this one here. If I were to go, so we're currently in this visual mode, if I switch to diffraction mode, takes a second to switch over. We don't see anything, right? And this is not because there's nothing, it's because the sample is so thick that nothing reaches the detector anymore. So if I now go back and go back to the crystal that I by chance found, well, I obviously selected it before. So if I go here, Hopefully it's still a crystal and didn't degrade or anything. There we go. And we see diffraction, right? So not only do we see the primary beam in the center, we see very nice diffraction to quite a nice resolution. So this is a perfect candidate to perform an experiment. And actually, this is what we're going to do now. Again, like I said, I prepared everything. So one thing I haven't said, so currently we have quite a wide viewing area, but if we were to collect data out of from all of this, we would get signal from the particle in the center here, but also the one in the top, and everything that we would see. So what we actually use is called a selected area aperture. And so this is basically a strip with a hole inside, and this is the area that we will select, or we will get our diffraction from, right? So only from this area we will get diffraction from. Yes, so in principle, this is quite easy to do. I've aligned this previously, right? But yeah, so we will just set our measurement conditions. Yeah, I can obviously talk about this for longer. But as long as all of this is set, we can just click Start Experiment, and then this will take a second to just load. Then hopefully. So it now just is automatic. It centers the diffraction pattern onto the detector so that it's, well, in the center, but it's easier to relate. Now it goes back to the starting point because I set basically an angular range to collect data from. So I think it was -60 to 60. And now the data collection will start. And this is the data collection. So we now rotate the sample, or like we rotate the holder all the way through from one side to the other, and we continuously collect data from this. Yeah. I'm doing this reasonably fast, but this is a typical data collection. So the entire thing takes maybe a minute. It's quite fast. Still, also in the interest of time, I pre-collect this obviously, and actually, so all of this, there's then some data processing involved, and from this data collection, actually from this crystal, what I got was this structure. I did this, I don't know, like half an hour before this meeting, and this is what is expected. So we have copper, we have carbonate, and we have hydroxide. So this is the expected structure for azurite. So, and this I can confirm this, that this was part of the sample. So this is actually from a colleague from a rock of azurite. So yeah, this is confirmed. Interestingly, it's almost done here. I collected from some other particles as well, and one of them was actually this, which is not this copper carbonate hydroxide, is copper oxohydroxide, so with a hydroxy and just oxygen on this side, and this is in the same sample. So if one were to do PXRD on this, there would obviously be the overlap of both of these. So I don't have PXRD of this sample, but there would be all of the signal corresponding to both of these on top of each other. But electron diffraction, it's possible to go to each of these particles individually and hopefully determine the structure of each of them, so that then one is able to distinguish between different phases. So even if there are several phases in one sample, that is also like found in nature. I mean, this is a natural. This is not synthesized, this sample, right? Yeah, one is there's at least a possibility to get all of these phases. Yeah, and yeah, in the meantime, the data collection has finished while I was chatting, and yeah, basically I can go back to the presentation. Yeah, basically that brings me to the acknowledgements. Like obviously, we thank all our colleagues, both in this office, but also so this National Electron Diffraction Facility is a collaboration or joint venture of Southampton with the University of Warwick. Obviously, we thank the instrument manufacturers who are very helpful with any issues we might have or additional measurements that we want to do. Other colleagues in the community that help with all sorts of problems. Everything is always a community effort, obviously. All of our users and collaborators, and yeah, thank you for your attention.
Thanks very much, Dan. Thanks, Pete. That was absolutely fantastic. Yeah, I really appreciated the the way you demonstrated that the problems and the practicalities of collecting these data, the detail you went into on the sample holders in particular. I'm sure that's the bane of many collectors' lives. So,
Indeed.
yeah. So folks, the speakers have kindly agreed to take questions. Happy for you to unmute yourselves and come on and ask a question, or to post it in the chat if you'd like me to ask it for you. So we've got a room full of people. So please feel free to jump in. I should say that in the world I operate in, we publish new minerals about 60 new minerals new to science are discovered every year, and in our journal we publish about 10 or a dozen of those. And so XRD is still very much the workhorse in terms of defining those. And in the other world I work in, it's in clay science, and powder diffraction is the workhorse in that. I mean, in all of its applications, clay science has got an enormous range of applications. To be still using this technique, 100 years in, as the main tool is quite something. So one question that occurs to me, and I know the answer to this, but I'm going to ask it anyway, which is in other techniques, infrared, for example, we use standards so that we can judge that the data we're getting out of our samples are comparable by the data you might get if you were using another machine or another operator, for example. Does that ever arise with XRD or ED? The need for standards, for example?
So at least for sort of single crystal, we use standards. So there's a couple of crystals that sort of when we're actually calibrating the instrument. So the standard crystal is cytidine, or we can use ambi, which is ammonium bitartrate. And there's some other ones as well. There's nilid as well. So they're known cells, and they're used for calibrating the actual instruments themselves. And I think there's other samples for powder diffraction. You've got as I say, the silica itself. We know exactly where the peaks appear, so just make sure that they are used and aligned to make sure, I should say, the angles are as we expect.
Sure.
Yeah, and similar for electron diffraction. So what I use, there's one can even buy grids where aluminium is CVD'd on top. So actually it would again give you powder rings, and again non-unit cell, and so you can exactly calibrate it. And this I do every week, every 2 weeks, to ensure that these cells are correct. And yeah.
Sure, gotcha. We've got a question from Ola Tundon in the chat, guys. So thanks to Peter and Daniel for the talk. Question is for Pete. He's currently interested in powder diffraction as his research is partly focused on determining bulk mineral composition of mud rocks. He's wondering if there are unique insights that single crystal diffraction can provide, which might potentially be missed by the powder diffraction method.
Shall I just go, because that's typically
Yes.
So actually, so every sample that I get, basically I usually ask, I even ask people to provide powder XRD patterns beforehand, to demonstrate that the sample is even crystalline. And what often can be missed in powder is small impurities or secondary phases that are where the peaks are overlapped by the dominant phase. So if the sample that the powder XRD was collected on contains multiple phases, actually electron diffraction is a potentially very strong method to determine each of these phases, which then make up and can be then, you could then do refill refinements, and even get proper bulk analysis of the different phases that the bulk sample contains.
Yeah, the mud rock sounds very familiar for people who are interested in reading about clay science, that's for sure. Seema also has a question. Is it part of your plan to create a database centered on electron diffraction?
That's not particularly needed to to be centered around electron diffraction, because what we use, so everything that's been published goes into the already established databases, the CSD and the ICSD. I mean, it depends who publishes it, right? But in principle, so everything that we produce here would go, depending on whether it's organic. If it's organic, it goes to the Cambridge Structural Database, which is more for organic compounds and metal organic compounds, like metal organic frameworks. Whereas if it's inorganic, it would go on to the ICSD, the inorganic database. It should, the CIF file itself contains information what the radiation source is. So there's one, as Pete mentioned, so it's basically very, very much human readable, but also machine readable. And so it should be clear that the diffraction was collected, so that the crystal structure was determined based off of diffraction from electrons and not X-rays or neutrons or whatever it is. And so there's not a particular one for electron diffraction, but it's just included in the big ones that already exist.
Okay, thank you. Question from Matteo. He probably missed it. He asks if the cryogenic holder in the ED can or cannot induce low temperature phase transition.
Yes, of course it can. So that if the sample is known to have a phase transition at I'm saying something at 150 Kelvin, and I measure at 100 Kelvin, I expect or there's at least a possibility. The issue with phase transition is always do not, so they might be at the same temperature, they might also not be at the same temperature, because obviously we're in vacuum, so the pressure is different. So this can have an effect as well. Maybe it's not the exact same temperature, but yes, one needs to be very careful with these things. And so yes, if there's additional information that there is a phase transition at the specific temperature, obviously I would adjust accordingly.
Okay, gotcha. Thank you for that from Matthew. And we have some other thanks in the chat, guys. I don't see any other questions, folks. If it's okay, oh, hang on, I beg your pardon. Somebody's been busy typing. Musa asks, his research focuses on analyzing chemical composition of solid minerals and fluid inclusions using Raman. How far can the XRD and SEM-EDS be used when some minerals are Raman inactive?
So in principle, I mean, EDS works on it is not dependent on bonding. So this type of elemental or these types of spectra arise anyway. So as long as a certain element is present in the sample, EDS can be detected, the X-rays can be detected. So yes, I mean, as you said, like actually, SEM-EDS would be my suggested way of going about this. As in the diffraction will not additionally help, but can. It depends on the question. If it's just about the included compound, then yes, SEM-EDS is just much easier to do. Yeah.
Okay, thank you.
And so any of the diffraction obviously needs the long range ordering. And if that's not the case, the diffraction won't give you anything additional. Doesn't matter if it's PXRD or electron diffraction or X-ray diffraction. There's other techniques that can do stuff with this or like non-ordered compounds. So there's an entirely different field about total scattering, where diffuse scattering is the part of interest. Hope this answers the question.
Okay, thanks. Seema also asks, is electron diffraction more expensive than XRD?
What do you mean? Do you mean the instrument, or do you mean like a measurement? So the instruments actually are rough, like the top end instrument. So a very top end instrument is more expensive on the electron side. But the electron diffractometer we have here is actually roughly on par with a very much top end single crystal XRD instrument that can be got now, but this is very much the end of the line, the most expensive thing ever for the measurement. So, I mean, Pete, you can answer how the National Service works in this respect.
So the National Service itself is free at the point of contact of that basically, as long as you can get EPSRC funding which is most academics within the UK, then sort of you can apply to use the service, and the same for electron diffraction as well. Now, in terms of sort of even just doing a measurement, so the one thing is single crystal, we will do effectively one measurement on one crystal in the end because of the time constraints, whereas Dan will do a collection on a grid, so there will be lots, because you saw how quickly one collection is, but will take sort of in effect the actual collection time overall will probably end up being the same, but he will have collected multiple data sets, sort of 10, 20, and then might need to combine them or at least look at them. Whereas generally within sort of single crystal is we know within 5-10 minutes of putting that we're actually going to have something that's either going to work or not. We don't ourselves worry about sort of something either being short or long. It's just, as I say, if you've applied and we have a management panel that said your science is good enough to work, we will run it, and so on. We have collaborations as well, but yeah, that's basically.
So I'd say people who don't have EPSRC funding, is there people from see, I'd say the UK who can pay for the services and so on?
So we do have a commercial service, and sort of people can contact. We are sort of there's only a certain number of people and so many days we can actually run sort of things, and we've got in effect our masters are EPSRC who sort of provide all the funding, but we've definitely got facilities to do some external things. It's on a completely case by case basis that we'd sort of need to know information about what's actually expected, because quite often sort of we will either temper expectations or things, because sometimes people will think, I need this information, I need to get this structure or something else, and actually we will say from what you provide, this is not going to be possible or something else, but we can definitely have that conversation, work it out to that stage.
Dan has kindly popped in the link for the website there for people who want to.
So in principle, just always contact us. It's always like it doesn't matter if national or international collaboration. Write an email. Yes. We're friendly. We don't bite. And then we can see also whether we're even able to give the answer to whatever question you have. Right.
Gotcha. Okay. Thanks, guys. Appreciate your offer to field queries like that. That's very helpful. Musa, I hope it was the MinSoc website you were looking for in terms of membership. I was the one that mentioned membership. I think we seem to have come to a natural halt on the questions, but as Dan just said, if you've got a question that you didn't get to ask now, feel free to flash off a message. It remains for me just again to say thanks again to the guys for this morning. I really enjoyed that. It's a long time since I went through it in that detail, and I really appreciate it, and I hope everybody else did as well. So if we can have one of those nice virtual rounds of yellow hand applause.